So hello, everyone. Welcome to this week's Autonomy Talks. This week is a great pleasure to have Andrea Bajcsy, who is a PhD student at University of California, Berkeley, working in the Electrical Engineering and Computer Science Department with Professor Anka Dragan and Claire Tomlin. Thank you very much, Andrea, for joining this early. It's early in California, so that's even better. Andrea's work focuses on human motion prediction and safe motion planning for robots that operate in close physical proximity to people. And today she will talk about her latest discoveries. And we are all really looking forward to hearing this talk. So go ahead, the stage is yours.
Thank you so much for that nice introduction. Yeah, so I want to start out by sort of just taking a step back and talking about how throughout my PhD, I've worked on a variety of robotic systems. I started out working first with manipulators, then I worked a little bit with quadcopters and aerial vehicles. More recently, I've been looking at ground vehicles. Now, I think what's most exciting about being a roboticist today is that all these robots that used to be only in our laboratories or primarily in our laboratories are now actually being deployed in unstructured real world environments. And so here you see some examples both from a lab that I work in, but also from industry that's deploying these kind of systems. Now, one thing I'll also notice is across all these examples, one key feature that you're going to see consistently is there's going to be people and robots operating in close physical proximity to each other. And as soon as that happens, what we really need our autonomous systems to do is to think a little bit more about how human behavior is going to evolve. More specifically, to plan effective behaviors, robots are going to need some kind of predictive model of human behavior to plan safe and effective motions. Now, one of the benefits of having robots deployed and access to a lot of data is the ability to start learning or using this data to build these predictive models. So here are some examples, both from academia and industry, of how this increase in human data can be used to start to develop predictive models of human behavior and put those predictive models into our autonomy pipelines to have our robots make better decisions around people. Let's take a closer look at how these kind of models can be built. So I'm going to use this running example throughout my talk of an indoor environment. We have one quadcopter here and one human. And a typical pipeline for trying to build these predictive models requires us to encode not only a notion of dynamics of the human, here denoted by FH, that takes in the human state and the human's control, but we also have to understand how the human makes control decisions so that we can roll out their future state through their dynamics and figure out where they're going to be in the future. Now, this decision-making process is exactly a modeling challenge that a lot of people try to tackle with data-driven methods. So for example, offline, I can spend a lot of time collecting data of how people move through this physical space, through this office building. And then here in this heat map, I'm showing you salient aspects of the room that people tend to move towards, like doors, tables, chairs. As soon as we have this kind of structure, we can build all these decision-making points, these decision-making aspects into our predictive model. And for example, write down some kind of stochastic decision-making model of how people choose their actions. So here, the probability of a person choosing their action is conditioned not only on their state, but also on which of these locations they're trying to get to, which is denoted by theta. Unfortunately, we don't know a priori which of these goals is the person actually going to be going towards at runtime. So when I deploy my robot, it has to somehow figure out which of these goals is the person going to based on observing evidence. And so here what we're going to do is we're going to place a Bayesian belief over these model parameters that we have extracted offline and use the actual human's behavior as evidence for which of these intents is the person actually sort of operating under when they're making their decisions. So here, since the person took a step towards this table, our Bayesian update is going to move probability mass on this table and say, hey, the probability of the person making actions based on this table is a lot more likely than it used to be before. After this estimation process, all we need to do is encode some kind of prediction scheme that can be then put into our motion planner. So here what we're really interested in is we're interested in finding the set of states that the human could possibly be at some future time, given that they're currently at some state. And I'm showing these distributions over states forward in time, visualized as these sort of clouds with higher pink areas as high probability states and bluer areas as lower probability states. Finally, a traditional pipeline that you might take to solve this kind of problem has to actually incorporate some kind of decision making in the robot. And to solve this kind of decision making for the robot, one common paradigm is to pose a constrained optimization problem, where the robot needs to not only abide by its own dynamics, minimize its cost. For example, in this case, the robot's trying to get to this goal shown in this blue dot in the lower right-hand corner, but the robot also wants to avoid collision with the human. And in order to do that, we're going to incorporate our predictions and essentially ensure that a robot never collides with these sufficiently likely states that are predicted by our motion predictor for the human to be potentially somewhere forward in time. All right, so I've implemented many of these throughout my PhD, and I'm going to show you one example, a really simple example of this kind of predictor in action. So we're going to see exactly the same example just from a top-down view on the right-hand side and a third-person view on the left-hand side. And here we have my lab mate Sylvia. In case you didn't know she was a person, she's wearing a human being shirt to really identify that. We also have a robot that's marked in blue. That's our quadcopter. And we have a really simple model, which only has a single parameter. The single parameter is shown in red, and it's just the door in our lab space. These waves that are going to be emanating from her are the predictions. Again, pink means high probability, bluer means lower probability. And in this case, when Sylvia is just going to be moving directly towards the door, when our robot's relying on this predictor, our predictive performance is really good. Our robot can use this predictor to make a really efficient decision, which just means let's take the straight line path to my goal, and everything's fine. The key problem here is that people behave oftentimes in really strange ways. So I have two examples that I really like to show that I found on YouTube of people behaving in ways that I might not have seen at training time when I've been, extracting structure in my human decision-making model. The first is this example of a person playing soccer on the side of the street. If I'm developing an autonomous system, an autonomous car that's trying to figure out, human pedestrian behavior, it's very unlikely I've ever figured out that people sometimes like to play soccer on the side of the road. An even harder example that I as a person can't even understand is this example where a person just decides to stand right in front of me, like right in front of the car for no good reason. And it's exactly scenarios like these where when the human behaves in an unmodeled way that our model cannot understand, there are going to be some safety implications for our robots. So in our lab example, we don't actually have a full autonomy pipeline. I can't recreate these examples I showed you above, but I can recreate a similar sort of instance in our simplified running example, which is now I'm going to spill some coffee right in front of Sylvia's path. This coffee spill is something that is not explicitly encoded in our predictor. In fact, you might even argue that it might be hard for the robot to even detect this with its sensors. And this means that when the prediction is like determining future states where the human could go, this predictor is systematically incorrect. And therefore, when the robot relies on this predictor and tries to plan a collision-free path, it actually can't because the predictor is always incorrect. And this leads to a safety violation here where Sylvia and the robot collide. Now, an alternative perspective is to say, well, since we don't trust these intents that we gathered, from all of our data, what if we just don't encode them at all? What if I remove all these intents? And removing this explicit decision-making now requires the robot to essentially just consider the physical dynamics of the human and ask, what are all of the possible actions that the human could ever take? And let me safeguard against all of these possible actions forward in time. Now, more formally, what this kind of predictor is called is a for reachable set predictor. It's popular in a lot of robust control theory communities. It's been applied also to some autonomous driving domains. And essentially what this just says is it says, give me the set of all states that the human could ever reach given some sequence of controls from time 0 to time t. And that's shown as these concentric red circles here based on the dynamics that I've written down here, which are these simple point pedestrian dynamics. Now, while safe, this kind of predictor, oftentimes when you put on a robot, ends up being inefficient. So let's see that in action here. We're going to see Now, a ground vehicle using this forward reachable set predictor. The forward reachable set is shown in these concentric gray circles shown forward in time, and our robot is shown as this green dot here with its motion plan in a receding horizon fashion here, shown in dark green. Now, when the robot's using these forward reachable sets for collision, it's going to be safe, but to avoid Ellis, my lab mate, as he moves forward, the robot actually has to leave the entire environment to be collision free. So as I mentioned before, we're surely safe here, but this kind of conservative motion predictor oftentimes results in inefficient motion, and it doesn't usually adapt online from new data. And so the core of most of my PhD has been really trying to reconcile notions of safety with data-driven human models that adapt online. So this is the question that's been driving most of my work. And throughout my PhD, I've worked on a variety of lenses on this kind of question. I've worked just on the human modeling portion and extracting these human models from human data. I've also worked just on the safety portions and updating safety controllers and safe sets online. But today I want to focus on exactly the intersection of these two philosophies in these two bodies of work here. And we're going to start out with how do we imbue notions of confidence and safety into these data-driven human motion predictors. All right, so let's return back to that data-driven human model where we extracted all these intents offline, we gave that to our robot's decision-making model, and now we want to maybe take a closer look at the structure of this decision-making model. So that P of UH given X and theta. Now, in general, you can choose many different structures. The typical structure that I've used throughout my research is this noisily rational Boltzmann distribution or softmax distribution that I'm showing you here. And it's a widely used model in both cognitive science, but also in robotics more recently. Now, what's nice about this model is it lets you encode how people make decisions through the Q function right here. So this Q function could be something that you compute via, for example, solving an optimal control problem, or it could be something that you learn, for example. But ultimately, this Q function here is encoding how good is it for the human to take an action from a state at given that they're trying to pursue some kind of objective theta. The other nice aspect of this model too is that it's not optimal. It doesn't say that people always behave according to the optimal set of optimal sequence of actions according to that Q function. It's going to be noisily optimal. And so the beta parameter here really encodes that noise in the distribution. It's typically fixed in traditional models here. And so again, intuitively, all it says is that people are exponentially more likely to be taking actions that are going to be aligned with their objective and helping them towards their objective than other actions. If we go back though to when our model was failing, and we take a closer look, the reason that our model was failing was because it was misspecified. So here, our model was incomplete because it didn't know about this coffee spill in the environment. And that meant that when we were relying on our predictor that didn't have a complete notion of how the person makes decisions, our predictions are wrong and the collision ended up happening. So to solve this kind of issue, we really need to be asking and answering two questions. First is, how can a robot detect that its predictive model is failing? And what should it do in response to be safe? Now, the very first thing that you might want to sort of solve this problem with is you might want to say, well, okay, we know that the full forward reachable set was safe. So what if this is the sequence of states that the human goes through forward in time as they're avoiding that coffee spill? What if we start out with our data-driven model and then we just choose a heuristic switching time to just switch into our forward reachable set predictor? Now, this might be okay as a schema, but in general, it's non-trivial to come up with this switching time, and choosing an incorrect heuristic can still lead to some unsafe behavior. In addition, if you stay in that forward reachable set regime for too long, you might, again, not be able to leverage any of that structure and have too conservative motions that ultimately come out. So there's actually something alternative that we really want. Maybe what we want is to automatically interpolate between that data-driven model that we constructed and our full forward reachable set predictor. What that really means is that while the human behavior appears to be performing well under our data-driven model, let's continue to rely on it. But the less and less it works, the less and less that model aligns with the data we see, let's start to trust the forward reachable set predictor more and more. This ultimately should help our robot trade off between both being safe and efficient. So how do we get this kind of smooth interpolation between the forward reachable set and our intent-driven model, given how the human is behaving? Well, to do this, we want to look back at our predictive model and recognize that there's that additional parameter beta that I described earlier as the aspect of this model that really varies the noise in this model. So how optimally does the human behave under their objective? If I choose a fixed value of beta, that's, for example, really low. Let's say I fix this value to be equal to 0. What's going to happen? Well, we're going to get the uniform distribution over actions out. And when we visualize what that looks like here on the right-hand side, what we're going to see here is the distribution, the state distribution at one time step, like so a snapshot of where the person can be forward in time. For a really simple model where this point human right here is trying to get towards this modeled goal shown in red. And if you'll notice the set of states that is being assigned some interesting non-zero probability, you see that that distribution of states starts to look like a tighter and tighter approximation of the forward reachable set. Now, this is nice because we know that when we start relying on this kind of conservative set of states, that our motion predictor or our motion planner as a result will be more safe. In contrast, if I choose a really aggressive, very high value of beta, what that essentially is going to do is place all probability mass on the actions that are optimal under our objective. So in this case, it's going to say if the person's here and they're trying to get towards this red goal, let's put all the probability mass in the direction of vectors that take them towards this red goal, which means that state predictions will be highly confident in the person moving essentially in a straight line. But again, our key idea here was let's not fix this noise, let's actually estimate it. So let's smoothly interpolate from that full forward reachable set to something in between, all the way up to this really confident model that really trusts those modeled intents that we extracted offline. And so the key idea here is we were going to really interpret beta as exactly a measure of model confidence. And we're going to use Bayesian inference to estimate this model confidence online based on observing how the human behaves. And then simply just by estimating this value of beta, we're going to get to start to scale between this whole spectrum of full forward reachable set predictor to data-driven predictor, just like I'm showing you here. So let's see how that actually works. For the sake of a running example, I'm going to keep beta discrete to a really small number of values here, 0, 1, and 10. 0 is the full forward reachable set, 1 is something in between, and 10 is really, really confidently believing in our data-driven structure. So after I put a belief on this, what's going to happen is when the human takes a step away from the modeled goal here, which is the door, then when we do our Bayesian update over this model confidence parameter beta, what essentially is happening here is we're going to be looking at each of these models that we have. We have forward reachable set model, beta equals 1 and beta equals 10. And we're going to ask ourselves, how likely is the data I'm seeing online under each of these models? Now, in this case, if you sort of think a little bit about how these probability masses are distributed, the model that places the most probability mass on a human doing something completely suboptimal, according to any of our goals here, which means running away in this case, is going to be that full forward reachable set model. And so intuitively, what's happening with our Bayesian update here is that if the human appears suboptimal under all of our modeled goals, all of our modeled structure, it's essentially giving us an indicator that the robot has the wrong model, and we should be switching to that full forward reachable set. And that switching is actually going to be happening smoothly here as we start to shift probability mass more and more towards beta equals 0 values. So here, after we do our Bayesian update, now the probability of beta equals 0 being the correct model confidence has increased. And the real beauty of this approach is that I don't actually have to change anything in my motion planning pipeline. So all that's going to be changing now is the shape of my predictions, but the resulting motion plan is going to automatically adapt. So if at the beginning we had this really confident set of predictions forward in time, but then the human runs away from the door, then after seeing some observations, our predictor is going to be shifted to that full forward reachable set, and the robot's going to plan this more conservative path around the human, therefore staying safe. So let's see that in our running example one more time. And so now it's the same running example with the coffee spill, but we're gonna see our new confidence-aware predictor in action. Everything's gonna look the same. Sylvia's just gonna be avoiding this coffee spill. But let's take a closer look at what happens when she deviates from the optimal path. Notice how those predictions blow up. And that automatically causes the robot to sort of take this like wider path around her. And it results in not too inefficient of a motion from the robot's perspective, but both of the agents are still able to remain safe. And this is despite the fact that the robot doesn't know at all about this coffee spill. This also helps in other scenarios. So here we're going to look at a scenario where there's two modeled goals, but one unmodeled goal. I like to call this the forgotten key problem, where let's say that you're, thinking about going to leave your house, but you forget your keys and you run back to go get them. So this dashed line here, this dashed circle is going to be where your keys are, but that's a location that the robot doesn't know about a priori. If you use the fixed model confidence predictor, as long as you're moving towards locations that the robot knows about, predictor does fine. But as soon as the human goes back to get their keys, an unsafe situation starts to happen. And you can see here very clearly that the predictions are systematically incorrect. They keep thinking that the human's just going to turn around and run back towards one of these other modeled goals. In contrast, when we use our predictor, it performs the same as long as the human is behaving, according to one of these modeled goals. But as soon as the human decides to go get their keys, our robot doesn't understand what this behavior is. And you can see this nice sort of blow up in the set of states that could possibly, that the human could possibly enter into, which results in this more conservative motion from the robot's perspective. Another domain in which this kind of confidence awareness really helps is in multi-agent interactions. So multi-agent modeling is really, really difficult. And this is actually one of the places where you might want to be leveraging a lot of data to exactly understand how people behave in crowded environments. But again, these models might be incorrect, or it might be really difficult to even extract them. And so a question that we were posing here was, can we put model confidence on top of a really naive predictive scheme in these multi-agent scenarios and still get good performance? So here we have two quadcopters. Here there's one and here's the other one. And we have two humans. So this is my lab mate Sylvia and Jaime. And what we're going to see here is each robot is going to be using a really naive predictor for each of the humans. So what they're going to essentially do is predict that each human independently of each other, assuming that they can physically go into each other. Obviously, this is a really silly model because people can't physically cross paths. But what's going to happen is when they start to interact in the center of this room and start to deviate from each other, the predictions will become more uncertain and the robots will become more conservative in their resulting motion. Additionally, there's one other element of sort of unmodeledness here, which is Jaime is going to be dancing this whole time. This was 4 a.m. And to keep himself alive and excited, he was dancing to some bachata. So those are all the unmodeled aspects that are happening here. And again, we're going to be using that model confidence estimation on top of this to make sure that each prediction is aware of what it doesn't know. All right, so here we've already seen that the humans have crossed paths and the robots have also avoided them. What I'm going to do really quickly is I'm going to play this video one more time, and we're going to take a closer look just here on the lower right-hand side to observe exactly how these distributions become more uncertain. So Sylvia is going to be a pretty optimal human right here, but Jaime is going to be noisy throughout. And so you can watch how those predictions end up being sort of blowing up right here when they interact. And then the robots continue on with their paths. The final thing I want to say here is, so far we've seen how this notion of model confidence awareness can help us in these prediction domains, but I've also investigated this in the case of autonomous driving, where, for example, you might have unmodeled potholes on the road or turnoffs that weren't modeled, and how that can really help you help your predictor become more robust. And the final scenario that's also really interesting is to think about how model confidence awareness can help in reinforcement learning domains, inverse reinforcement learning domains, excuse me. So here in this case, Andrea is trying to teach the robot to stay away from her physical body, but the robot actually doesn't know about what it means to stay away from Andrea's body. And in this case, model confidence can help the robot understand that it just doesn't have a feature in its feature set that can understand this kind of human data. And that can then help spur, for example, maybe a relearning process, or maybe the robot can ask a question to the human. But it's, again, this notion of monitoring and flagging when the robot knows that its model is just incomplete or not performing really well. All right, so with that, we've come to the end of the confidence-aware prediction and planning set. Now I really want to turn our eyes to analyzing these kind of models I get to adapt online. So what do I mean by this? Well, so far we've seen this confidence-aware predictor that, in this case, let's say we have this really simple Bayesian belief over either forward reachable set, so beta equals 0, or our intent-driven model beta equals 1. And if we start out with, for example, here, high prior that our model is pretty good, it's going to still take us some non-zero amount of time and observations to shift that probability mass onto beta equals 0, or a full forward reachable set predictor. And as soon as you have a predictor like this that has to wait to observe data online and adapt to this data online, what the model parameters change to and how quickly they change depends both on the robot's learning algorithm, in this case, the Bayesian update, and also on how the human actually behaves, so what data the actual robot sees. Now, these all have significant implications for safety and efficiency of the robot's decision-making because the model can change so significantly in light of new data. And so the key question that I was interested in here was, can I somehow start to analyze these kind of models that adapt online from human data? And what I mean here by analyze them is answer a few key questions about properties of models. So for example, one property that I would care about is I'd like to know what's the best case time it would take my robot to learn the human's true model parameters. Another kind of analysis question I could pose is, how should I initialize my robot's learning algorithm so that it can learn any parameter the fastest? Or I could also ask, what is the worst case time it would take my robot to learn these model parameters? I'm going to dive deep into how to answer each of these questions by using sort of candidate examples and candidate learning algorithms to highlight them. So here we're going to be using the confidence-aware predictor with our Bayesian estimation framework as our example for figuring out how to analyze best case time to learn. We're also going to take a look at gradient-based learning, where we're going to ask ourselves, how should we initialize our gradient-based learner so we can learn about human intent the fastest? And then we're going to also take a look at how these worst case time to learns can actually inform the design of motion planners. And we're going to be using an autonomous driving example there, where an autonomous vehicle has uncertainty about whether or not a human is going to be taking a left or going straight on an intersection. The ultimate thing, though, is that we would like to answer all of these questions, which use different learning algorithms and have different contexts, in one framework. So we would like one analysis tool that can answer all these questions. And to do this, we're going to take this perspective of treating the robot's learning algorithm as a dynamical system on its own, where the parameter estimate is going to be part of the state, and the human data is going to be the control input into this dynamical system. What this allows us to do is now answering what model parameters can the robot learn and in how much time reduces to answering reachability queries, which will give us the answer to when and what states can our dynamical system, in this case, our learning algorithm, reach. A lot of the things I'm going to be proposing here are going to have also strong sort of philosophical connections to, for example, state spaces used in POMDPs or in adaptive control. And there's also some nice connections between using Lyapunov theory for proving stability, for example, of gradient-based optimization. But here, the techniques we're going to be using are going to be using different kind of control theoretic tools. And we're going to be specifically looking at these kind of learning algorithms that use human data as input. So let's take a look at this. The first thing we're going to do is we're going to, in our framework, define the joint state space, which includes both the human physical state, but also our parameter estimate. So here, E is the general parameter estimate that your robot is maintaining, but it's going to take different forms in each context. So in the case of the motion planner and the case of the confidence-aware domain, the parameter estimate is going to be our belief. So here we're going to be maintaining the probability that our model is the full forward reachable set model, beta equals 0, or the probability that the human is taking a turn. And again, because these are discrete distributions with only 2 values, we can only maintain one of these values and recover the other. In the case of the gradient-based learning, since it's a point estimator, we're going to be maintaining theta, the actual parameter directly in our state. The next step is going to be to define our joint dynamics. This is really simple. We're just going to concatenate the physical human dynamics with our learning dynamics FL. The learning dynamics are just the update that we have our robot do when it gets new data. So in the case of Bayesian estimation, it's just going to be updating its Bayesian belief via Bayes' rule, which is denoted here on the upper and lower left-hand side. In the case of the gradient-based learning, we're going to be taking that gradient step and updating our parameter theta, just the way that we know and love how to do gradient ascent. Now that we have our dynamical system is really when we want to be asking our analysis questions, right? So what our analysis questions will boil down to is determining if our system, which is going to be able to start in some initial state, which again, Z0 here is going to be an initial state that includes not only where the human physically is right now, but also what our initial parameter estimate is. And we would like to ask, what human data will steer our learning algorithm into some desired set of parameter values, right? Because in order to be learning, we want to be learning some set of parameter values, which are going to be exactly encoded by this set L. And that will be the main way in which we're going to be encoding analysis questions. So for example, in the confidence-aware case, maybe one of the analyses we want to be asking is, well, I would like to know when my robot will be using the full forward reachable set. So what that means for L is going to be the set of all joint states which have a high probability on beta equals 0, the conservative model. And we want to know how long is it going to take us to learn that our model needs to be conservative. This target set is going to be taking different sort of shapes depending on what you're analyzing. For example, in the motion planner case, we're going to be having 2 sets. One, which is encoding high probability on the human taking a turn. So that's going to be what we would like to learn if the human is taking a turn. And the other kind of query we might ask is, what about if the person's going to go forward? So we have 2 sets here, L turn and L forward. But ultimately, with this dynamics and the set of desired values, parameter values L, we can now actually solve this kind of question of which human data are going to steer us to this desired parameter value via solving an optimal control problem. The optimal control problem we'll be solving can be solved via this discrete time Hamilton-Jacobi-Bellman variational inequality, which can be solved via dynamic programming. Now, what's nice about this formulation is that it neatly encodes a lot of aspects that influence our ultimate analysis. So first of all, L of Z in green, this little L, is going to encode how close our system is to the desired parameters we're trying to learn. So remember, L encodes the desired parameters we want our system to learn, and L is going to be a signed distance function, which tells our system how close are we to learning our desired parameters. The next component of this formulation is this inner min that I've highlighted in pink. Depending on whether or not you choose a min or a max, you are simulating the human data in different ways. So if we choose to put a min here, like I have right now, since we're doing a min over human controls UH, because the human controls are our data, choosing to min over the controls essentially says that the human is trying to help our estimator learn the true parameters as much as they can, because they're minimizing the value. They're trying to get us as close as possible to that target. In contrast, we can put a max here, and now the human strategy is to be deceptive. They're going to try as hard as they can to give us adversarial data, UH, that will make it as difficult as possible for our system to actually learn the true parameters. The last two components of this framework are big UT, which is shown here in yellow. That's going to be the set of all controls, i.e. data, that the human could possibly generate at any given time. And this is a discrete time problem, and the delta t here should be chosen in a way that represents how quickly you get observations, right? So this can be, for example, how quickly your state estimator runs, maybe your motion capture system. And again, that's going to determine sort of the inertia of your joint system and how quickly you can actually update your learning parameters. All right, so in each of these settings, we're going to be choosing either, for example, a min or a max. Most of the time, we're going to be using min. So for example, in the best case time to learn, the best case is going to be where the human is trying to give us the best data as possible to make our robot know that the forward reachable set model is what it should be using. And so in this case, we're going to have the human minimizing. But in the case of the worst case time to learn, we're going to choose a maximizing human because we want to understand these slightly adversarial cases that might take our estimator longer to have high confidence in the person, for example, going left or going straight. After computing this DP problem, we're going to result in the sequence of value functions parameterized by time. And one of the important properties I'm going to keep returning to when we're doing our actual analysis is this time to learn quantity. So we can obtain this time to learn quantity by essentially looking through our value functions, and for any given initial condition, Z0, asking yourself, what's the earliest time at which our initial condition Z0 is in the sub-zero level set of our value function? What this is going to do is it's going to capture the earliest time when our learning system can ever reach the desired parameters we seek to learn, starting from some initial Z0. Now, in summary, the basic procedure you go through to analyze any of these kind of questions I've put up here on the slide for any of these domains, no matter what your learning algorithm is to define your human and learning parameter dynamics. Then you're going to define the target parameters you would like your system to learn or analyze, solve your DP problem, and then you're going to extract your analysis questions, like, for example, your time to learn. And ultimately, the single analysis procedure I've outlined here can help us with answering analysis questions for any of these diverse application domains or learning algorithms. So let's take an actual look at what this actually means. We're going to start out with this best case time to learn for our confidence-aware predictor from before. Now we're going to have a complex environment here. Before I had mostly collision or mostly empty environments, but now we're going to be looking at this occupancy map that I've taken from AWS's bookstore world. So these are like bookshelves and tables. And we have a human here. And there's, again, a really simple parameter to our predictive model. It says that people like to move towards doors. And there's this one door here in the environment. What we really want to know now is, what is the best case time it would take our robot to detect that its model is incorrect and it needs to use the full forward reachable set? So what this really means is we want to extract the time to learn from our value function. And this minimum time to learn that we extract after solving our dynamic programming problem is going to serve as this lower bound, this best case on how long it would ever take for our predictor to become conservative, starting from some initial distribution over, for example, the two beta values, beta equals 0, which is the full forward reachable set beta, or beta equals 1, which is our data-driven predictive model. What I'm going to show you here is a heat map of these time to learns for all of these initial physical states where the human could be for a fixed uniform prior over beta equals 0, full forward reachable set, and beta equals 1, which is our intent-driven model. So intuitively, what's happening here is I'm showing you how quickly, what's the fastest that a robot could ever be confident that the that its predictive model is failing, depending on where the person starts in the state space. Blue indicates a really fast time to learn of only 0.9 seconds. Red indicates a high time to learn of 2.72 seconds. Now, what's really interesting is that we can extract some insights onto the difficulty of estimation depending on the environment. So, for example, in open spaces, it's really easy for the robot to estimate that the human model isn't behaving well. And that's because all the human has to do is run directly away from the door. And within a few observations, our robot will be very confident that the human definitely doesn't want to go towards doors. That's where we get that short time to learn of 0.9. But in highly constrained parts of the environment, like in this case in the lower corner, what's going to happen is now the estimation is more challenging because the environment constrains the type of observations the robot could see. So here, it might be unclear for the robot to determine whether or not when the human moves in these kind of patterns, is it because the human is not trying to get to the door, or are they trying to get to the door or trying to do something completely different? It's really difficult to understand. And that means it's going to take a lot longer for a robot to have high confidence on whether or not its predictive model is good. So ultimately, now what we've done with our analysis framework is figured out this lower bound in the time it takes a predictor to become conservative and safe. In general, there are many ways you can incorporate this kind of idea into a motion planner. So for example, you might want to impose some replanning frequency based on this, or you might want to design a new motion planning scheme that understands that in tightly constrained environments, maybe the robot should avoid those or be more cautious because estimation is just fundamentally more challenging. The second example is analyzing gradient-based learning. So we're going to look at the same physical environment. This is, again, our AWS bookstore environment. And the only thing we're going to change now is going to be the reward function, where now the human's reward function is going to be a linear combination of two features, some aspect which describes goal-seeking behavior. The goal here is this bookshelf over here, shown in this red circle, and obstacle-averse behavior. So trying to stay further away from obstacles. The other thing that we're changing too is that the robot's now learning via gradient-based optimization. So every time it sees how the human behaves, it's going to update its estimate of how much the human cares about trading off goal-seeking and staying away from obstacles. So just to dive a little bit deeper into the structure so we understand the analysis, the actual specific form of theta here is really simple. It's just 1 minus an unknown real number w and w. So again, what that means here is when we're trying to do our estimation, when we're trying to learn how the human trades off these two features, what we're really trying to ask ourselves is we're really trying to understand how we should choose an initialization of our weights, so initial W0, such that we could learn any true value, W star, of the human's parameter, right? So the human could be anywhere on the spectrum from completely ignoring obstacles to completely ignoring the goal. And we want to really figure out what we should initialize our algorithm to so we can learn any of these possible parameters the fastest. To provide a little bit more intuition for what's going on here, small values of W, we should always think of that as mapping to goal-seeking behavior from the human. Large values of W always mean obstacle-averse behavior from the human. So one more time, what's our objective? Our analysis question here is to figure out which W0 we should initialize our gradient-based learning with, such that we can have the robot learn any W star the fastest, any true human intent. And again, our optimal control problem is going to help us solve and answer this question, starting our computation sort of from each of these W0s. So here what I'm going to show you is a heat map of the minimum time it takes to learn any W star starting from a particular W0. So let's take a closer look. What's happening here? Well, let's say I initialize my gradient-based learner with W0 equals 0.25. What that means is that we're initializing our algorithm to assume that humans are goal-driven. Now, in the most extreme part of my learning, I would have to update my W0 all the way to have a value of 0.95 if the human is truly obstacle averse. This procedure, in the best case, is going to take us 2.2 seconds. Okay, what about the inverse? So what if I initialized assuming that the human is obstacle averse, and I tried to learn that the human actually is goal driven? In this case, to learn that the human is goal driven, it's going to take me 4.7 seconds to learn that. What's interesting here is you can automatically start to see that it is that different initializations are not created equal in terms of how quickly they let you learn humans' true intents. So if we want to answer the question of which W0 should we choose that minimizes the time to learn any possible W star, what we really should do is we should choose that value of 0.25. We should really encode this notion of goal-drivenness in our prior, because this value allowed us to reach any W star in the shortest amount of time. There's actually physical intuition for why this initialization is the best in this scenario. So if you look back at our environment here that I was showing you, and we take a closer look at this part of the environment where I was doing this analysis, this is the physical space that the human has to traverse when they're trying to move from their initial condition, which is right here, over here to their potential goal. What I'm showing you here in these two different trajectories is the optimal trajectory if the human primarily cares about goal seeking, and the optimal trajectory if the human primarily cares about staying away from obstacles. Now, intuitively, the discrepancy in how we should initialize comes from, again, the structure of the environment, which affects the type of observations the robot could see. So since the person begins in a part of the environment where their direct path is obstructed by obstacles, they have to navigate around the obstacles before they get to the goal. This means that our evidence is consistently biased to have the person always appear like they're moving mostly away from obstacles, and it makes it really difficult to disambiguate if they truly are goal-driven or if they're just obstacle-averse. So to counteract this, we can use this biased initialization of goal-seeking behavior, our initialization of 0.25, to bring down that time to learn and ultimately help our robot learn any possible W star value as fast as possible. The last example I want to quickly cover is how we can inform motion planner design. So here we are looking at an autonomous driving scenario. We have a robot vehicle in white and a human-driven vehicle in red. Now, here the robot wants to take a left turn, but this is an unsignalized intersection and it doesn't know whether or not the human car is trying to go straight or take a left. The robot's going to be maintaining uncertainty over these two options via a Bayesian belief. And now it has to somehow plan its motion in a way that, sort of safeguards against these two options or makes a, safe and effective decision. So one popular technique that has been explored in the literature and also both in academia and industry is this notion of contingency planning. This is a notion of motion planning that helps you deal with these kind of scenarios in this really nice way, where when you plan your motion plan, what you're going to do is you're going to safeguard against both events, so both the human going straight or left, for some short amount of time. So here in white, this is that short part of the motion plan that safeguards against the human going straight or left. After that time, you're going to branch at some branching time here, TB, and you're going to generate two contingency plans. One, which is blue in the case that the person actually ends up taking a turn. One that's red in the case that the person actually is going forward. So in general, this is a really nice framework because now you essentially have your robot being conservative for some short amount of time, after which ideally it should have no more uncertainty about the human's behavior, and then it should be able to choose one of these plans to make an effective decision. Unfortunately, choosing this branching time is really non-trivial. And if you choose it incorrectly, it can lead to, again, safety violations. And so in this case here, I've shown you a branching time that's too short. And I spend a lot of time with these kind of simulations. So after a lot of time observing situations like these, perhaps I as an engineer could come up with a reasonable branching time. But in general, it's really hard. And these branching times depend on a lot of things like the environment, the configuration, the initial conditions. And so that really begs the question of how should we choose these effective branching times to get this like initial safe behavior when the robot has uncertainty, but then branch and commit to a good, effective motion plan afterwards. And so we can actually start to ask and answer this kind of branching time question again in our analysis framework. We're going to use our analysis tool to compute a worst case time to learn for each outcome first. So remember when I said we had two of these sets, these one set that represented us trying to learn that the human is going to go straight. Well, using that kind of set allows us to then extract this worst case time to learn that the human's going forward. We can also run another computation, which gets us this worst case time to learn that the human is going to take a turn. Again, why worst case? One thing I like to think about is the scenario where, let's say you're trying to take a left turn, but you really pull all the way into the center of the intersection. If you pull all the way into the intersection before taking a left turn, all of that evidence of you going straight is going to make the robot really confident that you're going to just go forward. But it's only after you pull all the way into the intersection do you take that turn. And that really is that adversarial kind of problem that I'm really trying to capture here with this worst case time to learn. And again, it's not even that adversarial in the sense that the human isn't like backing up or like, doing like loop-de-loops in the center of the environment. It's just actually even taking slightly suboptimal paths makes the estimation a lot more difficult. All right, so after computing these two time to learns, one for the human going straight, one for the human going left, to choose a branching time that's safe and ensures that the robot commits to a contingency plan only after it has certainty, we're going to take the max between these two time to learns. So basically that's just saying is we need a safeguard against either of these two options that is the hardest for me to estimate. In this case, it's going to be the scenario where the human takes a left turn. That's actually the turn that's actually the scenario that's more difficult for your estimator. And so TTL turn is going to be dominating this max. What that now means is that when the robot is moving around, it commits to the correct kind of contingency plan and safely maneuvers around the behind of the other human agent and sort of starts to make progress towards its goal while also avoiding the human. These are all here shown as receding horizon plans of length 8 seconds. All right, so with that, I've come to the end of the sort of core of my talk here. We've talked about confidence-aware prediction and planning, where we were able to detect and safely react to misspecified human models by estimating this model confidence parameter online. And we've also talked about how to analyze properties of human models that adapt online by leveraging ideas from reachability theory. I have one last small section, which is sort of like future work related. Maybe can I ask if I have sort of 5 more minutes, or should we stop here and do questions?
I actually think that people are free to leave, but I would be interested in you talking about these things for 5 more minutes. There's no issue.
Okay, maybe, I mean, I can take a few questions if for those of you who might need to sort of leave imminently. So maybe if anyone has any questions, I'm happy to take them right now really briefly.
Right, yes.
Okay, well, in that case, I will continue. Amelia, did you have any questions?
No, well, probably people who have questions also want to stay and listen to the rest of your talk, right? So
sounds good. All right, let's go through it. So the next part is very sort of it's a lot more high level, and it just sort of was the result of me thinking a little bit more and taking a step back from what we've been talking about today. So I focused in this talk a lot on these like vehicle domains where we really had good notions of what it means to be safe, right? Safety means collision avoidance. But in many domains, like on the left-hand side here, in manipulation or in close sort of physical interaction collaboration, safety, just as defined as collision avoidance, may not be necessarily the right thing we want to be thinking about anymore. And so what I want to do is quickly spend some time just starting a discussion with all of you about what it means to start thinking about safety beyond just collision avoidance. So why is this important? I mean, 2 examples I like to keep in mind are first, this crowded hallway. I'm sure all of you have experienced this when you've gone to school or to an airport. sometimes physical collisions between agents are inevitable and actually not bad, right? In this tight environment, it's actually not bad if I'm bumping into other people. It might be a little bit annoying, but it might be necessary for me to make it through this crowded hallway. Additionally, physical collision actually sometimes might be useful. And actually I might want to I might want to instigate physical sort of interaction with my other agents in my environment. Like in this scenario here, where this adult is teaching a child how to pour some olive oil. And again, if we only are thinking about safety as physical, collision avoidance, these kind of scenarios might be impossible for us to solve or even to analyze with our current tools. Now, in the context of robotics, what are the classical properties of safety many of us sort of think about? Well, so far what I've been talking about here, we really want to have, for example, like really stiff controllers that are very precise. We get good tracking trajectory performance. And what that really means is that now if I can track my trajectory really well, then as long as my trajectory is collision free, then hopefully, I'll never hit the human and I'll always, sort of be really efficient when I'm making my motions. And while this is good, again, because of these collision avoidance properties, in the case where the human, for example, does come in contact with the robot, like here, my lab mate is pushing on our Kinova robot that we have in lab, assume that the human actually, bumps into the robot or maybe wants to interact with it. Suddenly, this kind of stiff controller is no longer desirable. A bump might actually be quite painful, and a physical interaction might be just completely undesirable or unpleasant from the human's perspective. And so now when we're talking about this kind of scenario, maybe a really, really stiff kind of precise controller is no longer desirable anymore. And so there's a whole line of work here that is not necessarily mine. It's from the literature here on investigating, for example, compliant controllers. And this makes now collisions safer between the human and the robot, and also enables, in general, this really intuitive way for the robot to respond to external forces. It does induce, for example, error sometimes in how the robot's going to behave, but that actually might be desirable in these kind of interaction scenarios. Now, the other thing to think about is, okay, is it just sort of reactive? Is it just control level safety that we want to rethink? And I'd argue that there's another layer up that we should sort of think about when we're thinking about expanding our notions of safety. And that's really something that comes into play when we think about what the robot should be doing after coming into physical contact with the human. So here I'm going to show you a quick example of my lab mate Ellis. And this is our robot that we have in Anka's lab. And our robot here is trying to move this cup that's holding its hand down towards the table for Ellis. Now, what Ellis really wants is Ellis wants the robot to keep this cup really close to the table because he doesn't want the robot to spill whatever's inside. But the robot's original trajectory that it's planning, the trajectory that is optimal under the objective it's been given, is going to take this really wide sweeping path. And so as the robot moves and Ellis sees that it's not behaving correctly, Ellis is going to grab the arm and try to sort of push the robot down to show it like, hey, I want you to keep the cup lower, closer to the table. When we see this kind of interaction, our autonomous system is nicely behaving compliantly when experiencing this kind of external force. This is nice because, again, the robot isn't necessarily hurting Ellis when it's strongly resisting him. And Ellis is actually able to give it some kind of interesting input. But there's another level here to what we want our autonomous system to do in order to safely respond to Ellis. And that is really think about why Ellis, who is on his own an autonomous system, who makes decisions based on his own objectives, what it really wants the robot to be optimizing. And so here what we really did in this line of work is we really thought of human interaction as, again, evidence about what the robot should be optimizing. So in this case, when Ellis pushes on the robot and moves it downwards, what the robot should be estimating or learning is saying that, hey, these external forces aren't just random. They aren't just something I should compliantly sort of react to. I should actually update again my notion of my objective and align that better with the human's input. In this case, the robot should learn, hey, I should keep the cup lower, closer to the table for the rest of the execution. And that's actually what happens here. When the robot re-optimizes the new objective it's learned after Ellis interacts, it's going to spend the rest of the time close to the table and keeping the mug the way that Ellis wants. where in contrast, if we just had this nice compliant controller, it would sort of bounce back up and have the robot sort of go up and down as Alice keeps trying to push it down towards the table. And so I want to just quickly end here and sort of ask ourselves as a community, you know, who are interested in safety, what does safety really mean in collaborative learning? Right, there might be notions of physical safety that we care about. Just like I said before, you know, can the robot respond to interaction smoothly? Are we ensuring that the robot never, for example, learns objectives that lead to unsafe trajectories? But there's also important components of psychological safety. Things like, has the robot learned what the human wants it to learn? Does the robot ever learn to perform undesirable behaviors? And I think ultimately these are just a few questions that we might be asking when we start to think about what safety means in collaborative learning. But ultimately, I'm very excited about these new possibilities for what it means to combine notions of safety and data-driven human modeling in these interactive environments and interactive scenarios that go beyond just collision avoidance. I want to quickly end with a thanks to all of my fantastic collaborators, and first and foremost, obviously my advisors, Claire and Akka. As many of you know here, working on robotics is really hard. You need a huge team of great students and people supporting you, and these are all the fantastic people who have been involved. If you're interested in any of the papers I described today, here's a list of publications, some references, and with that, I will end. Thank you so much for your time.
Thank you very much, Andrea. Very, very cool talk. Are there questions from the audience?
Andrea, my first, first of all, thank you very much for the talk. It's a very, very interesting work. The one thing that I think of when I look at the work on prediction and interacting with the robot and trying to figure out what humans will do is that I think that in the model that you presented, the humans are essentially oblivious to the presence of the robot, right? So what happens if that is not the case? I remember I started, I did some work on this when we were working on the go-kart. Our first go-kart was driving in pedestrian areas. And actually what we found is that, with the model that we were using, is that the safest way for the go-kart to drive through a pedestrian area, for a crowded area, was to go at max speed, blaring, like a honking like crazy.
I love that. I love that.
which kind of like it makes sense, right? So humans would not be very happy, right? But they would be safe, right? Yeah. So, but so in a sense, how would you incorporate the fact that the humans, well, I mean, in any case where safety is a concern, I would imagine that humans will actually pay attention to this robot that is moving towards them, right? Or could potentially hit them, right? And alter their behavior. How would you take that into account?
Yeah, so I think the sort of most popular paradigms, or there's two perspectives on that. I think you can take the perspective that maybe some people who are more data-driven only inclined would take, which is, look, let me learn, for example, robot policies based on a bunch of examples of how agents interact with each other. So I can make my robot behave like other people do in crowds. But the other perspective that I think has been really popular, and I know that several students in Claire's group are very excited about right now, are game theoretic formulations. And I think those nicely capture exactly these kind of interaction effects between multiple agents. They obviously don't necessarily, there's a lot of work that needs to be done to scale these kind of games. There's also a lot of work that needs to be done with games that have uncertainty too, because how do you know what the other agent is optimizing? And how they're interacting with you? Are we playing general sum? Are we doing zero sum? Like, I'm not really sure. So I think there's a lot of open questions there, but that's something that I'm very interested in doing next. So far, my work hasn't focused on exactly these kind of interaction, like close interaction modeling scenarios. Mostly what we focused on is thinking about, if you have the incorrect model, what should you do? And that could still be applied to game theoretic settings. Like maybe if you learn that one of the strategies you've encoded in your game just is doing a really poor job at actually explaining how the other agent's behaving. Maybe you want to switch the full forward reachable set, do something like that. And there's also another thing that I'm really excited about is in the analysis portion of my work. One nice thing about these reachability formulations, that HJB variational inequality, is that you can put other agents into that optimization problem. So before we had, minimization over the human control, but now we can actually say minimization over human control, but also, for example, minimization over robot control. So the robot is also trying to take actions that influence the human, and ultimately both of their actions are going to be influencing whether or not the robot can actually estimate well what the human's going to be doing. So that's a nice example of that is going to be in autonomous driving, like a lane merge example, where you might need to figure out whether or not you want to slow down as a robot to detect whether or not the human is going to be turning into your lane. So far, you're absolutely correct. I have not thought about that. I think there's different philosophies, and I think we have yet to sort of figure out which philosophy is the one that helps us reach the best notions of safety for these kind of interactive scenarios, whether they be purely data-driven or game theoretic or something in between.
But can't you include some kind of reaction to the robot in your model of the human?
Yes, exactly, and that's what would eventually happen in the game theoretic formulation. Like if the P of UH given XH and theta now depends also on XR, the robot state, and maybe UR, the robot's control. So now you have to learn.
Right, but I'm thinking of, to avoid the game theoretic setting, because there are complexity implications and things like that. What if you fix the policy, right? Which in a sense is what we did, right? So, but then you can get these results like the one that I was telling you about, right? So essentially what we said is that if the car is going very, essentially, the pedestrian will stay away from some region of unavoidable collision with the car, right? So then the car goes very fast, and then the car, essentially always gets it right away, right? Or or if the car signals that like a danger by honking, right? So then also the pedestrian stays away, right? So in a sense, but in that case, if you fix the response, then you can get an answer, right? So now the problem is that whether or not that's an answer that you like, right?
So maybe, so here's a sort of a first pass engineering solution that I would do. Maybe what I would do is I would compute a few policies. Like maybe what I would do is I'd have one scenario where I treat the human as oblivious to the robot. Another one where maybe I have some fixed policy of how the human reacts. They're always going to run away from me. And another one where the human, maybe tries to somehow coordinate with me. And then maybe what I could do is I could do that classical robotics thing and say, let's put a distribution over that. Let's estimate which of those are, and then just plug those into my model and do prediction.
Right, exactly. Right. So essentially a model that includes a reaction to a fixed reaction, or doesn't have to be a fixed reaction, has to be a fixed policy that reacts to it. Can be part of your collection of models in a sense.
Yeah, that's a great point. And I think that'd be really interesting. Yeah. I like the example a lot, though, of the blaring the cars. That's so good.
I love it too. Unfortunately, we couldn't write the paper, right? Because it kind of was, really, but in a sense was insightful, right?
Yeah, and I think it does get at the core of a lot of things that I think people who work on prediction and planning really have to answer for themselves, which is, when does prediction really matter, right? Sometimes reactive strategies might be enough. Sometimes you really need to be anticipatory and use a really good predictor. Sometimes you need to be aggressive and just enforce your policy on everyone else. And too bad that's what we're going to do now. And I think that having an agent really realize what scenario is it in is probably what we really need to have. Because I, as an autonomous system, as a human, I know when it really matters if I ignore other agents, or when it really matters if I'm going to impose my strategy or not.
Right. So, okay. So I don't want to, monopolize the time here, but it may actually be the case that sometimes you want to be a little bit of a jerk, right? And just go in, full speed and, sorry, I'm in a rush, right? Some other time, but if you do that all the time, then, people will not like you, right? If you do it when it's really useful, maybe people will accept that. And that makes me think of the karma work, right? That Andrea and others in the group are doing. I don't know, our Andrea Bajcsy.
Yeah.
I don't know if you've ever seen that, but so maybe the case that sometimes you may be willing to act a little bit, in a selfish way, and given that you act in a selfless way, sufficiently, often, in a sense of that, people are not, don't react badly to your robot or something like that.
Yeah, I completely agree. And I think another dimension of this, which I didn't touch on in this talk, is sort of the human factors aspect of it. So if I do deploy my robot, and maybe let's say like 1% of the time, it's kind of a jerk. But that 1% of the time is really important for it to be able to like get the person in your car to the store fast enough. The question is like, is that 1% worth it to other people in the environment and the person inside? Because like it might be really optimal from a planning perspective. Maybe everyone actually does get to their goals and they're actually safe the entire time. But is that really desirable from like a social perspective? And I think that's a separate question that requires human factors analysis. But typically, I think so far I focused on, and I think a lot of people have focused on, like primarily just can we be safe and efficient at with our modeling paradigm, not whether or not people will accept a robot that is 1% at a time a jerk. I mean, that's what a lot of the HRI community focuses on. So I'm sure they have some insights there too.
Okay, thanks.
Yeah.
Are there any other questions? It doesn't seem so. So Andrea, I think you left the contact in case people need to.
Yes, I'll also paste it in the chat because I stopped.
All right, yeah. That's good if somebody wants to ask detailed questions. Thank you very much. It was a great talk. I will contact you once the video is ready.
Sounds good.
And good luck for your next steps.
Thank you. Thank you so much for having me. This was a pleasure.
Thank you. Bye-bye.